So now so you've got your group 2 elements, or इसमें कि these are your group 2 elements. There's radium at the bottom. They kind of all have the same electronic configuration, which is that they have 2 electrons in the outer shell, and those 2 electrons are in the s subshell. ठीक है, याद रखना group 2 जो होता है वो s2 होता है. ठीक है, so if you write the electronic configuration of any one of them, it's going to come out to be like calcium would be 20 electrons, so that's 1s2, 2s2, 2p6. 3s2, 3p6, and then there's going to be 4s2. So outer shell jo hai, it has 2 electrons. So anyways, reactivity increases down the group. Why does it increase? Kyunki it becomes easier because they have to lose electrons. A metal always has to lose electrons to react. So reactivity increases because you have कहीं यहाँ पे लिखा हुआ है, नहीं लिखा हुआ. So the reason reactivity increases is that it becomes easier to lose electrons. Why does it become easier to lose electrons? Because you've got a bigger atom and more shells. So the shielding increases, so you have more shells as well. तो ये दो reasons है जिसकी वजह से it becomes easier to actually lose electrons. तो मतलब if you look at Mg and Ca, तो Mg is 3 shells, while Ca would be having 4 shells. तो ये let's say Ca. तो Ca size में bigger होगा, ठीक है. So down the group, the ionization energy decreases. If we link this with ionization energies, both atoms, they kind of have 2 electrons in their outer shell. But since Ca is bigger, तो Ca के जो 2 electrons होंगे वो काफी दूर होंगे. They would be very far away, and it would be easier to remove electrons compared to Mg. So hence ionization, we can also link this with ionization energy, that it decreases. Down the group. ठीक है, ये सारा क्लियर है रिएक्टिविटी वाली बात? Is this clear? Yes or no?
Yes, sir.
अच्छा, फिर ये कि अच्छा ये गलत लिखा हुआ है, ये करेक्ट कर लेना. वो नोट्स दिए हुए उनके अंदर एक 2 चीजें गलत थी, ठीक है, नोट्स में. वो एक जो मैंने पहले कहा था वो करेक्ट कर लेना कि सोडियम का जो मेल्टिंग पॉइंट था वो बहुत ऊपर वो स्केच हुआ था. दैट शुड बी लोअर, ठीक है, वो एक करेक्ट कर लेना. और एक ये गलती है नोट्स में, व्हिच इज वेयर डिड इट गो, रिएक्टिविटी से बिल्कुल नीचे, दैट्स रिड्यूसिंग पावर. दिस शुड बी they don't get, I mean they're oxidizing agents basically. तो इसको चेंज कर लो कि it's not reducing power, it's actually oxidizing power. तो वो मैं ऊपर करके ना करेक्ट करके लिख लेता हूँ कि the oxidizing power increases, or they become better oxidizing agents when you go down the group. So down the group, they become better oxidizing agents. Because they're able to lose electrons easily. The top one, ठीक है, तो ये एक बात है, ये काट लेना नोट्स में, ठीक है, make sure you correct this. So down the group, they become better oxidizing agents because it becomes easier to lose electrons. For barium, it's very easy to lose electrons. So anything that gets oxidized, that loses electrons, it's a good नहीं, सॉरी, ये फिर से मैंने गलत लिख दिया. ये काटना नहीं था, ये काटना था. Increases. वो ठीक थी, पहली वाली बात ठीक थी, ये डिक्रीजेस वाला पार्ट ठीक है. सो ये मैं फिर से करेक्ट कर रहा हूँ. अच्छा, so I'm going to explain this again. So down the group, it becomes easier to lose electrons. So barium over here at the bottom, it's going to lose electrons very easily because it's a bigger atom. So down the group, it becomes easier to lose electrons. So anything that gets oxidized is acting as a reducing agent. Anything that gets oxidized is acting as a reducing agent. So this is a very good reducing agent. The top one is a very bad reducing agent because smaller atoms, they don't lose electrons easily. So they don't get oxidized easily. So it's very hard to oxidize beryllium compared to barium. So when you move down the group, it becomes easier to lose electrons. So they become more easily oxidized, which means they become better reducing agent. So the reducing power increases. Adani, I'm not sure. एक second. So उसको waiting room. Yes.
Why did you include group 18 next to group 2?
Just 1 second. Acha, where did I include group 18? Acha, this one. You're talking about this one, right?
Yes.
That was when we were doing electronic configurations. I told you there was another way, like you can write the whole electronic configuration, right? Or there's a simpler notation, which is that 1s2, 2s2, 2p6. I mean, this is the entire electronic configuration of calcium.
Oh, I understand.
Okay, so I mean, it's always harder to actually. It takes a long time to write the whole thing. So you just don't write the first part. You cut that out, and that is basically how many? 18 electrons. 18 electrons is going to be, I think, argon, and it's going to be argon, and the outer shell would be 4s2. Okay, so that this is that notation. I say reducing power. Is this thing clear?
Yes, sir.
अच्छा, तो ये correct कर लेना. Decreases की बजाय it's going to be increases. अच्छा, then the melting boiling points decrease due to larger ionic radius. We did discuss this earlier as well during metallic bonding that bigger ions will have a lower charge density. They'll have a bigger ionic radius, so they will have a lower charge density. They're not going to attract each other very strongly. So we did this in metallic bonding. These are also metals. So remember, now imagine this going down the group. Like we can just copy the same ones. Now imagine going down the group, you become a bigger ion. The charge remains the same, but you become a bigger ion. Bigger ions have a lower charge density. They're further away from each other, which is why the lattice formed would be very, very weak. Relatively speaking, it's going to be weak. So this is what happens. They have the same number of delocalized electrons. The charge is the same, except that the size of the ion or the ionic radius increases. So we can add that the charge density decreases over here. Is this clear? Clear?
Yes.
Achha, so this is group 2 metals have higher melting and boiling points compared to group 1. So I mean, group 1 is not in our course, but group 1 had very low density. But anyways, group 1 is not in our course. But they do have higher densities relative to group 1. Now, the first thing is the reactions with water. Now, the reactivity is increasing down the group. So what happens is they're becoming more reactive. So the reactions become more vigorous. So the top one is going to have a very slow reaction. Magnesium doesn't really react with cold water. It reacts very, very slowly. And you get, it ends up forming a very weak alkali. So the pH would be around 8. It's going to be a very slow reaction and very slight bubbles, very slight effervescence. I mean, there's hardly going to be any effervescence. There might be 1 or 2 bubbles getting formed after like 20, 30 seconds. So almost no effervescence. So with steam, the reaction is really fast and it forms a white powder. We did that in period 3 as well. And when you go down the group calcium, the reaction becomes vigorous. Strontium and barium, it becomes more vigorous, and it also becomes more alkaline as well. The reason it becomes more alkaline is that down the group, the solubility of the hydroxides increase. So solubility of the hydroxides of group 2, they increase. They become more soluble. So they also become more alkaline down the group. Magnesium hydroxide is not very soluble, while the other ones, they become more and more soluble. Yahan pe likha hua bhi hai, they become more soluble. About calcium hydroxide, there's another point written that calcium hydroxide is partially soluble. So it's going to form a white suspension. Okay, so the appearance of calcium hydroxide in the solution would be a white suspension because some of it will dissolve, some of it will not dissolve. Just like dissolving NaCl, imagine you're dissolving table salt. Some of it doesn't dissolve, some of it dissolves. So you'll see the white salt, white powder floating around. So calcium hydroxide is like that. So that is the reaction with water, which you have to remember. About calcium hydroxide appearance, that's going to be a white suspension. And this is just an extra point that remember this, always remember hydroxides and oxides are they can be interchangeably used. Whenever you have a hydroxide and you heat it, then it's going to decompose and it will form an oxide and a water molecule will be released. And if you add the water molecule back again, it's going to form the hydroxide back again. So usually at higher temperatures, the hydroxide is going to decompose and it will turn into an oxide and vice versa. So this one over here, this is an extra point that has nothing to do with the above. It's calcium oxide. If you add water to it, so calcium oxide, you add water to it, it turns back into calcium hydroxide, but that's a very exothermic reaction. And the calcium oxide will start to hiss and the water will start to boil when you add calcium oxide to water. So this is just a minor point that you have to remember. So moving on. This is about, the first point is about beryllium oxide. Remember, beryllium oxide has the same properties or similar properties as aluminum oxide, which were aluminum oxide is unreactive and it's amphoteric and it's insoluble. So beryllium oxide questions don't usually get asked about beryllium oxide, but remember, when you think about beryllium oxide, think of aluminum oxide. It was amphoteric, it was insoluble. We did aluminum oxide in period 3. And it was also very unreactive. So beryllium oxide is going to be something similar to that. And aluminum chloride was also covalent. Beryllium chloride also happens to be covalent. The reason these two are kind of similar is, and they have similar properties is, because they have similar electronegativity. So they have similar electronegativity. What that means is that if you have group 3 and there is group 2, then aluminum is over here in group 3, like there's boron, and then there is aluminum, and beryllium is over here. Now remember this, that in the periodic table, if you move in this direction, on this diagonal, the electronegativities are very similar. Why? Because up the group electronegativity increases, and when you move to the left, the electronegativity, it decreases. So aluminum and beryllium, they're very similar in electronegativity. So Al and B and beryllium have similar electronegativity, which is why the bonding is kind of similar as well. The bonding is decided by electronegativity, whether it's going to be ionic or whether it's going to be covalent. So the bonding is also kind of very, very similar. So they have similar Is this clear? ये clear है कि नहीं?
Yes, sir.
अच्छा, फिर ये कि solubility का आ गया. Remember, down the group the solubility increases. MgOH2 is very less soluble, and when you move down the group, the solubility of the hydroxides, they become more soluble. Now about this, you have to remember the pH. Remember the pH of calcium hydroxide, strontium hydroxide, barium hydroxide, they are going to be strongly basic. Barium hydroxide would be very basic. Calcium hydroxide would be less, but the pH would all be greater than 10. Magnesium hydroxide is the one that's very less soluble, so it's hardly soluble. So the pH is closer to 7. It's around 8 or 9. So remember, if you were to estimate the pH, these three are greater than 10, while that one is less than 10. And since we are talking about solubility, I'm going to state the solubility of other group 2 compounds. The solubility of sulfates. So I'm going to write down the solubilities of sulfates. Now, the solubility of sulfates also decreases down the group. And here's so the solubility of sulfates it decreases. So this one is insoluble. Usually strontium sulfate is also insoluble. And MgSO4 is soluble. So I'm going to write aqueous next to it. And calcium sulfate is kind of partially soluble, partially insoluble. So I'm just to show that it's slightly, so some of it would be solid and some of it would be aqueous. About solubilities of the other compounds. Remember, carbonates are all insoluble. Group 2 carbonates are all insoluble. Carbonates as well as phosphates are all insoluble. What about chlorides? Group 2 chlorides, bromides, iodides, they're all soluble. And nitrates are soluble. So you must know this is O-level solubility. So you must know which compounds are soluble, which ones are not soluble. So it's only in hydroxides that there's a trend. The hydroxide solubility increases down the group. The sulfate solubility decreases down the group. So you have to remember which sulfates are insoluble, which hydroxides are soluble. And then we talk about the decomposition of carbonates and nitrates. So you've got a carbonate, let's say it's magnesium carbonate, it will form magnesium oxide plus carbon dioxide if it decomposes. If you have a nitrate, it will decompose to form metal oxide plus NO2 plus half O2. So you've also done these reactions in O-levels, the decomposition of a carbonate and the decomposition of a nitrate. The only thing is that down the group, the carbonates as well as the nitrates, they become more stable and they become thermally stable, so that the decomposition temperature increases. Like over here, it's much harder to decompose barium carbonate. It's easier to decompose magnesium carbonate. ठीक है? ये चीज clear? इस पर कोई question नहीं है. Is this clear?
Yes, sir.
अच्छा, अब the important thing about these carbonates and nitrates you should remember is okay, the bottom two are really hard to decompose because they have a higher decomposition temperature. And the same applies to nitrates as well. Like I don't know if we have like group 2 nitrates decomposition. You don't have to remember the temperatures. if one second. So decomposition, they gave temperatures for carbonates. Actually, anyways, the decomposition temperatures for nitrates are not quoted, but they're kind of similar. The important thing that has to be remembered is the reason I've written Bunsen flame over here is you should have an idea of how hot the Bunsen flame is. It's 1000 degrees centigrade. So a Bunsen burner cannot decompose strontium carbonate and barium carbonate, but the top two, they can be decomposed using a Bunsen burner. So they'll give you questions related to this, that they will heat it on a Bunsen flame. So remember that bottom two will not decompose because their decomposition temperatures are a lot higher. ठीक है, clear?
Yes, sir.
Yes.
Now, this over here is the reason why decomposition becomes harder down the group. The reason for that is, so I'm going to quickly do the reason. For example, here's a magnesium ion. Now, magnesium is a small ion because it's up the group, so it's +2. So it's got a higher charge density. And here's my carbonate ion. Carbonate is C double bond O. So that is what carbonate looks like, CO3. And these oxidants have a -1 charge. So that's a carbonate ion. The carbonate ion and the Mg ions will get attracted to each other. And that is what MgCO3 is. Mg +2. And I've got CO3 -2. So they are both attracting. So they are both attracting each other. And that's the force of attraction between the two things is your ionic bond in MgCO3. Now, if I draw barium carbonate, the only difference would be that barium is going to be a bigger ion. That's it. So if I were to draw underneath this, if I were to draw barium carbonate, this को हम change कर लेते हैं. Let's make this Ba, and it's +2, and this ion size would be a lot bigger. ठीक है, that's the main. So that's the main difference. So I've got magnesium carbonate and I've got barium carbonate, and I'm moving down the group. The size of the ion increases. That's the only difference. So what is stated over here is that this one is a lot harder to decompose. I mean, this one over here is a lot harder to decompose, and this one is easier to decompose. पहले तो बताओ कि which one is going to make a stronger bond? Smaller ion or bigger ion? Who makes a stronger bond? Who's going to have more?
Smaller ions, right?
Smaller.
The smaller ions have more attraction, right? So they've got more
Yes.
attraction. They've got more attraction because they've got a greater charge density, right? So more attraction, higher charge density, which means that the bond of MgCO3 should have been stronger, right? And the but they're saying that the decomposition is a lot easier. And we are saying that the bond is really strong. So it's got a higher charge density. So it should have been harder to actually decompose it, right? Because smaller ions, they make stronger bonds. But the thing is that the attraction of magnesium ions is so strong that what it does is that it has such a strong force of attraction that what it ends up doing is that it's got a very high polarizing power. So the carbonate ion gets polarized. Like this is what happens, that the attraction is so strong that the oxygen ion with its electrons gets pulled very, very strongly towards Mg. And oxygen, instead of sharing electrons with carbon, its electrons, they end up with oxygen, with the magnesium over here. They get pulled towards magnesium. Is the idea clear?
So it
Yes.
forms magnesium oxide.
Exactly. So the thing is that even though the attraction is stronger, and it should have been a strong bond, but the decomposition actually becomes easier because the smaller ion has a very, very strong attraction for the electrons of oxygen over here. And the electrons, they get pulled. So the electrons kind of get pulled towards magnesium. And you end up with, I mean, this part over here turns into carbon dioxide. And this part over here turns into magnesium oxide. Hence, the decomposition is easier. Is that clear? Which is why the decomposition temperature is so low as well. Is this clear?
You begin to decompose the products, magnesium oxide and carbon dioxide.
Pehle tha you had magnesium carbonate, right?
Yeah.
The point I'm trying to make is, and we discussed that that the attraction between the carbonate and
Okay. Never mind. Yeah, I understood.
okay. So the point is that the smaller ion attracts the other ion so strongly that the other ion kind of breaks down, it decomposes. Over here, that's not an issue. A bigger ion is not going to attract the electrons from the other ion that strongly. So which is why the carbonate ion would be kind of stable. So this is what is described over here in these lines, that down the group, the ionic radius increases. So charge density decreases. Hence, the ion polarizing power decreases. Like this ion over here is not going to polarize the carbonate ion. And it's going to be less polarized down the group. So the carbonate or the nitrate ion is going to be less polarized down the group. So which is why it's going to be harder to decompose, because during decomposition, it's not the bond between them that's breaking, it's the carbonate ion that's decomposing, that's turning into carbon dioxide. So that's the main reason for this. That's about it. We're done with group 2. It's you just have to write uses. Remember, MgO is often used as a ceramic. Why? Because it's got a very strong ionic substance, and it's got a very high melting point. So that's MgO. So you make tiles out of MgO for furnaces, etc. Well, उसकी properties लिख लो. It's got very high melting points, and because of the smaller ion, the ionic bond is really, really strong. Now, calcium carbonate is a very common. It's known as limestone, and you make lime out of it. You decompose it. You make lime out of it. What do you do with lime? Lime is often used to make. It's often used in cements, concrete, etc. So it's one of the ingredients. It's one of the ingredients for cement. Calcium carbonate was also used in making steel. If you remember steel, iron extraction, the blast furnace reaction, limestone was used to remove impurities. Limestone neutralizes acidic soil. You add lime as well. Limestone is basically chalk. You neutralize acidic soils with it. We can add an equation for that. How does it neutralize acidic soils? That if you add either calcium oxide, the H+1 in the soil are going to react with it. The H and O will turn into water, and calcium ions would be produced. I mean, you can have a complete acid. So it's going to be, if you add HCl to HCls, then it's going to form calcium chloride. So this is the ionic equation. If you have calcium carbonate, 2H+1, again, a calcium salt would be produced, water and carbon dioxide would be produced. So that is, you make cement out of lime mortar, plus you add sand and water, etc. You mix it with other stuff, including gypsum. Now, I'll also add one thing that, I mean, the binding ingredient for cement is lime. Like this is what makes cement strong. Lime itself is not strong. What happens is that lime reacts like if you have cement, over time what will happen is that the lime, because it's a base, it will react with the acidic gas that's in the atmosphere, which is carbon dioxide, and it will turn into calcium carbonate, which is the strongest substance. So when you make concrete, the paste that you have initially, that's basically lime with gypsum, etc. But then over time, it's going to absorb the carbon dioxide, and it will turn into calcium carbonate. So this is how a cement sets, that it absorbs. It absorbs, so basically wet lime absorbs CO2 from air and turns into CaCO3, which is concrete. And CaCO3 is your strong substance that is formed at the end. TK, is this clear?
Yes, sir.
और बाकी आपके ना, you have your flame test. Remember the flame test, Mg is white flame, bright white flame. Calcium is brick red, strontium is red scarlet flame. Barium is going to have an apple green flame. So that's all about group 2. So these are just a few things, not much. Thermal decomposition, who's soluble, who's not soluble, bases, which ones are alkaline, which ones are more soluble, which ones are less soluble, and the reaction with water. That's about it. So we can start with a bit of group 17 as well. Aisha, I did send the notes in the group. Can you check? Did I send them?
Yes, yes, but they don't have the writing that you did now.
Acha, this one. Nee, for this one, I'll share the board link. I'm going to share it over here as well. But don't open it. Open it on your laptop or on a desktop, not on your phone. On the phone, it's but the phone mates, they don't open properly. Sorry, everyone in meeting. Actually, this is the board link. Just don't open it on your phone. The thing doesn't really open properly on phone. Uske upar bhi I'll add. So, very quickly, let's do. I think we were. So on the third page, we have inorganic. So the first part is you've got. So the first part is you've got group 17, which are your halogens. So fluorine, chlorine, bromine, and iodine. Fluorine is a gas. Chlorine is a gas. This one is a liquid, and iodine is a solid. The term that they refer to this is that the volatility, it decreases down the group. They become less volatile, which basically means that the boiling points and melting points are increasing when you become less volatile. It becomes harder for them to evaporate. Now, the melting and boiling points are increasing down the group. Why are they increasing? Because they have only van der Waals forces or temporary dipole, induced dipole. This is what's happening, that you have a fluorine molecule, you've got another fluorine molecule, and they are completely non-polar. So the force of attraction that exists is existing. Why? Because of temporary dipole, induced dipoles. Due to random fluctuations, sometimes this side would be negative, this side would be positive. And the negative side will repel the electrons, and the negative side would become this, and this one would become positive. So the dipoles would be fluctuating. They would be, because there's no atom that's electronegative. So it's only going to have van der Waals forces, and van der Waals forces are weak, which is why mostly they're going to have low melting and boiling points. But van der Waals forces increase with size. So if the molecule size increases, the van der Waals forces, they become stronger. So which is why they become stronger. And the other thing is the colors, they become darker as well. You have to remember the color. Fluorine is almost colorless or very pale yellow. Chlorine is greenish yellow. Bromine is orange brown, and iodine is a blue black solid. अच्छा, इसके बाद है कि you've got bond strength. So remember about bond strength, we have studied that smaller atoms, whenever you have smaller atoms, they make stronger bonds. So they make stronger bonds, and there are lots of reasons for that. One of them is when you have a smaller atom, they are closer to each other. So obviously, if they're close together, when you are closer to something, the attraction is going to be stronger. Like if you have two magnets, if they're very far apart, then there's going to be weaker attraction. If they're like really next to each other, there's going to be stronger attraction. So more attraction for shared pair of electrons. So more attraction for shared electrons. And if there's more attraction, there's going to be more orbital overlap. They're going to pull each other's electrons more strongly. And we can also write that the bond length is smaller as well. And the atom is less shielded. The nucleus is less shielded. So the nucleus is going to be attracting the electrons even more. Smaller atoms, they will have a lot stronger attraction for electrons. So they will attract each other's electrons with a lot more strength. So remember, smaller atoms, they always make stronger bonds. So bigger atoms are going to form weaker bonds. Iodine is a big atom. Smaller atom, the bond strength increases. Chlorine is an even smaller atom. And then fluorine over here is a problem. Fluorine is an anomaly. And the reason fluorine is an exception is कि वरना तो ये बात ठीक है, but otherwise there's this one exception. F2 is an exception.
High charge density?
नहीं, F2 के अंदर issue है. नहीं, there's not going to be, because remember charge density is going to be used for ions, not for molecules, because an atom in a molecule doesn't have a charge. Is that clear?
Right, okay.
अच्छा, fluorine का issue ये है कि fluorine is a small atom. So there should be stronger attraction for electrons. I mean, there should be. So it's like a really small atom. The nucleus of fluorine doesn't have a lot of shells. So it's like right next to the electrons that are being shared. So up till this point, the attraction is going to be really strong because the nucleus is right next to it, and the shared electrons over here, it's a small atom, and there's going to be a very large orbital overlap. So it should be a strong bond. But the reason it's a weak bond is that fluorine has a lot of lone pairs. Lots and lots of electrons in the outer shell that are not doing anything, that are completely full orbitals. So what happens is that in the case of fluorine, the fluorine molecule is so small that the lone pairs, they come very close to each other. And if they come really close to each other, then there's going to be repulsion created. So for the fluorine atoms to stick together, I mean, why were they sticking together? They were sticking together because they were shared pair of electrons that were being pulled or attracted by both nucleuses, right? This one, so they were both pulling those electrons, but that force of attraction is not enough to keep the fluorine atoms together, because there's a lot of force of repulsion because of those extra lone pairs. These lone pairs are repelling these lone pairs, so there's a lot of repulsion that's created, which kind of weakens this bond. Is that clear? You clear?
Yes, sir.
ठीक है, बाकियों को जोहा इज क्लियर, रायना, मरियम, मिनाहिल, आयशा क्लियर है?
So your voice is breaking.
अच्छा, नहीं, is it breaking for everyone? Can you hear? Can you guys hear
Not
me?
anymore. Yes.
Acha. So I'll just explain this again, that the fluorine nucleuses of the two atoms should have been very strongly attracted to the shared electrons, but they're not, because there's another factor, which is that this fluorine has a lot of lone pairs and this fluorine over here has a lot of lone pairs, and those repel each other. These electrons repel these ones, which is why it's very hard for the two fluorine atoms to stay together, because there's a lot of repulsion created. So that's the reason why fluorine is an anomaly, because of the smaller size, the lone pairs come right next to each other, which kind of makes it very impossible to sort of put them together or keep the two atoms together. Is that clear?
And sir, what about spin pair repulsion? Does that have anything to do over here as well?
Nee, not spin pair repulsion. Like, spin pair repulsion was within the orbital. We don't care about that over here.
Okay.
Okay. But the idea is clear, right? You've got, I mean, this doesn't really happen in other atoms. Like if you have a hydrogen molecule, it usually doesn't happen with other atoms. So if I have a hydrogen molecule, they share electrons. So a hydrogen atom shares electrons. So they only have attraction, right? There's no reason for repulsion, because it doesn't have any lone pairs. This one doesn't have any lone pairs. So the nucleus of this hydrogen and the nucleus of this hydrogen are all attracted to these electrons. So in other molecules, you don't have this scenario. You don't have a lot of lone pairs, and the lone pairs over here and the lone pairs over here will repel, which kind of weakens the bond. So is that clear? This scenario usually doesn't happen with other atoms or molecules. Clear?
Yes.
Mastige, let's continue in the next class from here. Just remember that the nitrogen and sulfur part, that is almost the same that you did in O-levels. We'll just finish this quickly and then we'll be done with this within organic. All you have to do is you have to memorize this stuff and remember this stuff, the colors, the boiling points, the melting point trends, etc. Everything. Okay, make sure one way to do that is print these notes, keep them with you at all times, and just go through them like 2 or 3 times a week. Just go through them. Eventually you'll memorize that till the exam. Okay, you don't have to make an effort right now. Just keep on like 2-3 times a day, 2-3 times in a week. Just go through these notes so that eventually at the end of the day, till the exam, you'll be able to memorize this stuff. Okay? Yes.
Okay.
Do we have another exam in March? Like a big
I
exam?
think there's going to be a mock exam.
Oh, is it towards the end of March or the beginning?
They didn't tell me anything, but I think it's probably going to be like in the second week of March, probably.
It's in the end.
It's
From
at the
21st.
21st, eh? ठीक है,
Yeah.
21st se. Then we have more time, ठीक है. चलिए ठीक है. Okay then everyone. Take care. Allah Hafiz.
Allah Hafiz.